Good afternoon. Welcome once again to a new installment of Dave Does Math at Home. This particular video is going to be part 3 of our section on polynomials, section 3.2. The last video covered the basics of what we need. The fact that we're looking for end behavior, we're looking for local behavior. End behavior is what happens when x is really big, what y looks like when x is big, and local behavior is your x and y intercepts, which happen when you set variables equal to 0. So we're going to pick up right where we left off with another example, going through the local behavior and end behavior of this polynomial. This one we have today is x cubed minus 3x squared minus 4x plus 12. So this is a cubic polynomial with 4 terms. We're going to have a good time factoring this one. Let's get right into it. For the x-intercepts, that means I need to set y equal to 0. And when I set y equal to 0, I get 0 equals x cubed minus 3x squared minus 4x plus 12. And this is a cubic equation that we need to solve by factoring. So to factor something with 4 terms, you split it right down the middle, factor by parts. You can pull an x squared out of the first piece. What's left here is an x minus 3. Out of the second piece, I'm going to extract a negative 4 and be left with an x minus 3. Because these x minus 3 pieces match, I can factor the x minus 3 out of this term and this term. From this first term, I'm left with an x squared. From the second term, I have a minus 4, after I pull the x minus 3 out to the front. So this is a linear factor, and it's done. This is a quadratic factor. It can still be factored more. So I'll go one more step and say that this is x minus 3 times x plus 2, x minus 2. These are the difference of squares. These are the 2 factors that x squared minus 4 turns into. So I have 3 factors. Each factor should give me a solution. My solutions here are x equals 3, x equals negative 2. Oh, ooh. This color has some scent to it. And x equals 2. But again, I don't really want to express these as x values. These are my x-intercepts. So x-intercepts are points. I want to be expressing these as points. I'm going to say that my x-intercepts are 3, 0, negative 2, 0, and 2, 0. These are the intercepts down at the bottom. And that's it for the x-intercepts. Next up, we need some y-intercepts. Y-intercepts happen when you set x equal to 0. Setting x equal to 0, generally speaking, is much, much easier than setting y equal to 0. All we got to do is say that y equals 0 cubed minus 3 times 0 squared minus 4 times 0 plus 12. To be completely honest, if you want to skip almost all of this, you can. All of these terms are going to end up being 0 except for 12. You can just skip straight to y equals 12 if you like. But again, this is an intercept, so I should write it as 0, 12, not just as a number. 0, 12 is the intercept. So I have 3 x-intercepts and a y-intercept. All that's left is for us to discuss end behavior. When x is big, y looks like x cubed. All of these other terms, the squared term, the linear term, the constant term, those terms are so small that they might as well not even be there. When x is big, these guys are all just rounding error. They don't really count for anything. only the leading term matters for end behavior. X cubed looks like this, but I'm not interested in this local behavior. All I care about is I can't erase that with my finger. This blue is heavy duty. This is an intense marker. I don't really care about the local behavior in the middle. All I'm interested in is the end behavior. So down to the left, up to the right, that's the end behavior. I call this one disco right. So, got my x-intercepts, got my y-intercept, got my end behavior. I'm going to copy this all down up here, and then erase it so that I can draw a nice big graph. Three, 0, negative 2, 0, 2, 0, 0, 12, disco right. Okay, let's make ourselves a graph. There's 12 up. We'll go 3 out on each side. So I know I have a point here. I have a point at positive 3, and at positive 2, and at negative 2. These are my 4 intercepts. And if I'm doing disco right, it needs to be going down this way and up this way. So it looks like it's a pretty straightforward connect the dots kind of issue. We'll go up here, I'll hit this one, we'll come back down, pick up that one, connect with this arrow. It's headed up and to the right. That's it. There's your graph. All done. In less than 8 minutes. That's all it takes to graph a cubic polynomial. I'm going to do another example. Perhaps a more interesting example. Let's do y equals, let's make it negative first of all. Negative x cubed plus 10x squared minus 25x. Let's do this one. There's a couple things going on here that were not going on in the last problem that we should talk about. First of all, this is the first problem we've done where the leading coefficient, that's the coefficient on the leading term, isn't 1. The other examples we've done have all had a 1 here in front of the leading term. That's made things relatively easy. If you have a non-trivial leading coefficient here, the best thing you can do for yourself is just get rid of it immediately. When you start looking for these x-intercepts, you set y equal to 0, which gives you, I need a new marker. This black is not holding up. 0 equals negative x cubed plus 10x squared minus 25x. So when I say get rid of it immediately, I mean from here, the very first thing you can do is multiply both sides of this equation by -1. On the left, the thing equals 0, so multiplying that by -1 is not going to affect anything. It's still just 0. Multiplying this by -1 is going to flip all of the signs. So this will give me x cubed minus 10x squared plus 25x. And now I'm back to having this positive 1 as my leading coefficient here for the purpose of factoring this. I haven't actually gotten, it's still part of the polynomial, the original polynomial, and I'll need to consider that when I'm thinking about end behavior. But for the purposes of factoring it, you can just sort of get rid of it, make it go away, as long as you change the other signs as well. So to continue factoring, I have 3 terms. They all have x in them, so I can start by pulling the x out. X squared minus 10x plus 25. Now the x is out front, and this, what's left in here, can be factored normally. So looks like x minus 5 and x minus 5 should do it. So my intercepts are x equals 0 and -5 and -5. One of those is repeated twice. We need to talk about what that means. For now, we'll just say that I have 2 intercepts. Oh, sorry, not -5, positive 5. 0, 0, and 5, 0. These are the 2 intercepts that I come up with when I factor this. The y-intercept I'll do in a different color. The y-intercept means that we set x equal to 0. So that'll give us y equals 0, 0, 0, just 0. So we have the point 0, 0, which we already knew about. We were definitely going to get a 0, 0 intercept here. But it's good to show that we thought about it. Lastly, we need end behavior. When x is really, really, really big, only the leading term matters. So we'll say that y looks like negative x cubed. It's not just about the leading exponent. It's about the entire leading term. Negative x cubed looks different than x cubed. So whatever coefficient is here, you have to think about that for the end behavior. You can't just take the x piece. Negative x cubed looks like this. But again, I don't care about all this local stuff happening in the middle. All I'm interested in is what's happening on the ends. Going up to the left, down to the right. I call this one disco left. So, got my intercepts, got my end behavior. Let me write that up here. 0, 0, 5, 0, and disco left. Now we can erase most of this, start drawing a graph. Kind of wanted that last line here. Let me bring that back. 0 equals x times x minus 5 times x minus 5. Okay. So let's start this graphing process. Okay. I have an intercept here, I have an intercept here. Just go left means I'm going up, down here, and down over here. So here's where we run into a bit of a problem. If we just start connecting these dots like normal, like it kind of looks like this should come down and this should go up, and now I'm in trouble. Because I need to ultimately go down to the right. Disco right means I need to be going down here. Or sorry, disco left means I need to be going down in this direction. But I'm above the x-axis. There's no other intercepts. I can't just cross it over here. If I cross the x-axis over here, then there would be an intercept there, and I'd know about it. And there are no more intercepts. So here's sort of the weird thing that happens. This intercept, this factor is repeated. This intercept, 5 is on this list twice. That means that it doesn't cross here. It bounces. This is called multiplicity 2. Multiplicity 2. Things that have even multiplicities are going to bounce off the axis. Things that have odd multiplicities, this is multiplicity 1. Multiplicity 1 is kind of what we're used to in the other examples. It'll cross at a multiplicity 1. It'll bounce at a multiplicity 2. I'm going to talk more about that in the next video. I think this camera's about to cut me off here. So, part 4 is incoming.